Okay, so welcome back everyone. So in today's lecture, we are going to extend the gradient descent algorithm to the constraint setting. So the problem that we want to study in this lecture is defined here. So we have a smooth function f. Now we also have a constraint set C, and want to minimize the function f over the constraint set C. Okay. So by constraint, we mean any point you pick, any w you pick, it must be in the constraint C. Okay, so we need to handle the constraint. So this is the difference from last lecture where we only want to minimize the function f and there is no constraint C. Right? A typical application of this constraint minimization problem is the so-called white box attack of machine learning models. Okay, so in this example, we have a classifier f. So x here is the input image. It's given to you. And then you have a classifier. This classifier is represented by the vector w. Okay, for instance, if you have a neural network, then w will be the weights in that neural network. And we have C classes. Okay, for instance, I can have two, and I want to classify an image into either dog or cat, right? And because f is a vector, it has C entries, and each entry basically indicates the relative probability of the image x being in that class, right? So fk is a probability for x, the image, to be classified into the class K. And here for white box attack, we are assuming the model is already given to you. In other words, W, the weights of the classifier, is given to you. And we're not interested in improving the classifier. To the contrary, we are interested in fooling the classifier by constructing a new image. So what we're going to do is we add a perturbation delta to the image x such that if you predict on the perturbed image x plus delta, okay, you pick the maximum probability, right? This is your prediction on the perturbed image. And we want the prediction on the perturbed image to be different than the ground truth class of the original image. So if I give you an image of cat, right, and I change the image a little bit, and naturally you would expect the image should still be a cat. But I change the image in a way that the classifier or the machine learning algorithm will actually classify x plus delta to be a dog. Okay, so this is the idea behind white box attack. So here by white box, we mean we actually know everything about the model, the algorithm, the machine learning algorithm, or the classifier. Okay, later on, when we talk about derivative-free optimization, we are going to see how to do a black box attack where you do not have access to the model. Okay, for now we assume you have you have access to everything. All right, and these perturbed images are called adversarial examples. Right? There's a lot of interest in the machine learning community in constructing or defending against these adversarial examples. Okay, so we can formulate the white box attack as exactly a constraint minimization problem. So we want to minimize the probability of predicting the true class Y, and by adding a perturbation delta, right? And we don't want the perturbation to be too big, because if you add a huge perturbation to the image, of course you can change the image, change the prediction, but then you change the image a lot as well, right? We don't. We want the perturbation to be insusceptible. Okay, so we want delta, the norm of delta, the size of delta, the perturbation, to be small, to be smaller than epsilon. And we also have this constraint because each image after normalization, each pixel value is between 0 and 1. So we want the perturbed image to be still an image, right? Its pixel values should still between 0 and 1. So now you see we have this constraint C. This is how much you can perturb an image, right? The perturbation data has to be in this set such that the perturbed image is indeed a legitimate image and the perturbation is small, right? Okay, so now if we assume the function f is smooth, then we have exactly this constraint smooth minimization problem. Okay, and the algorithm that we're going to see in a minute can be used to construct these adversarial examples. In fact, it's one of the most effective algorithms at the moment for constructing adversarial examples. Okay. All right. So we have a function we want to minimize, and we have a set. We have a constraint set. So how do we minimize the function over the constraint set? There is a very cool result in the univariate case. If you have a univariate convex function, so meaning that you only have one variable, and you have a convex set C. The set C is also convex. To remind you, we defined convex function, convex set in the first lecture. Okay, so if you are not familiar with these terms, you should go back and check the definition. So in the univariate case, what you can do to solve the constraint minimization problem is, first, you just drop the constraint. You pretend there is no constraint at all, and you find the minimizer of the function f, right? So how do you solve this problem without constraint? Well, you can use gradient descent that we discussed last time, right? And once you find this minimizer, this unconstrained minimizer, then you just project to the constraint set C. Okay, by projection, I mean you just compare with A. If your unconstrained minimizer is smaller than A, you just bring it up to A. And you compare to B, the right-hand side, as the right endpoint as well. If your unconstrained minimizer is greater than B, then you bring it back to B. Okay, and this is what I mean by projection. It will be clear in a minute. Okay, so we have this very simple result in the univariate case, and it's actually quite convenient. So you should memorize this, and also you should prove this by yourself because it's relatively easy. Just go back to the definition of convexity and you can prove that. Okay, so that's a cool result, and in fact we're going to see how to apply it on the next page. So okay, so now the next question, or the natural question, is, can we actually generalize this idea, right? And the answer is, unfortunately, is no. So if your constraint C is not a convex set, even in the one-dimensional case, then this theorem is no longer true. If the function f is not convex, then this theorem is not true. And if you go to high dimensions, like 2 dimensions, you have 2 variables, even when the function f and the constraint C are convex, the theorem is still not true. Okay, so we really have a very special theorem in the univariate case. So, and I'm not going to give you examples here, but you should be able to construct counterexamples for each of the claims here. Okay, and if not, feel free to ask me during office hours. Okay, so we cannot, in the high dimensional case, we cannot just ignore the constraint, right? So we have to do something else. And there is a very natural thing to do, namely that I do my gradient descent step. This is my gradient descent update, right? And then I'm going to choose my step size such that after the update, I am still in the set C, right? So whenever I'm doing a gradient descent step, I only go as far as to the boundary of the set C. I never go outside of the set C. The problem is, for this algorithm, even though it looks natural, you can easily construct counterexamples to show it will be trapped in meaningless points. Okay, so this is a counterexample where we show that if you apply this algorithm, it's not going to work at all. Okay, and it turns out that the important thing here to do is you first need to jump outside of the constraint set C, and then you use projection to bring yourself back to the constraint C. Okay, so that leads us to the definition of projection, right? So if I do an update and I go outside of the set C, so my point is not feasible anymore, but I have to be feasible, right? I have to satisfy the constraint. And then what you can do is you can go back to the constraint set, right? And we do this through the so-called projection. And the projection is defined with respect to a constraint set C. So we define the projection over point W, an arbitrary point W, to the set C as the point Z in the set C, and Z is closest to W, right? So if I draw a picture to illustrate this, basically we have, this is my set C, and I have a point W. Then if I do a projection, I basically find a point in C that's closest to W, right? This is one. I can have another one. For instance, I can take another candidate. I have 2 points, and obviously the red point is closer to W, right? So this is how we define the projection. It's the closest point in the set C, okay? And it's quite easy to show the projection always exists. It doesn't matter if the set C is convex or not, we always have a projection, okay? And geometrically, it's very clear that if the given point W, if W is not in C, then the projection should be at the boundary of C. Okay, this is quite clear geometrically, right? Because you cannot be inside C, because if you go inside C, you have to cross a boundary, right? So any point that's inside C has to have a larger distance than the point on the boundary. Right? That's clear geometrically. And the other thing that's clear is that if we do, so this time I'm going to draw a non-convex set. If we take a point that's within the set C, if W is already in C, then the projection of W to C is just W itself, right? Because W is close to itself than any other point, right? So this is all clear geometrically. And it is also clear that if your set C is not convex, like in this case, it is possible that the projection is not unique. Okay, and this is best seen maybe from a one-dimensional example. So if I have an interval, I have another interval. This is my set C, and it's not convex, right? Obviously. But then if I take a point that's sitting in the middle, then if you want to find the closest point in C to this orange point, and it's obvious that you have two choices, right? This one and this one. So the projection is not unique for non-convex sets. In fact, there's a very cool result that shows that the projection is unique if and only if the set C is a convex set. Okay, so if the set C is convex, you have a unique projection. There's only one projection. And if your set C is not convex, then you could have more than one possible projection. Okay? All right. So next, we have an example to illustrate the idea. The first example, projection to the cube. This is the example that we mentioned before, the white box attack. Okay? If you choose the norm to be the L infinity norm in the white box attack, then the projection for the white box attack can be reduced to the example here. Okay, so you can actually use this to implement the white box attack for the L infinity norm. And the main technique here to solve this projection is to realize, first of all, the projection is defined in this manner, right? For given point gamma, I want to find delta, and delta satisfies this inequality constraints, right? And the first thing I do is I can square the objective function without changing the minimizer, right? This is what we mentioned in the first lecture. Okay, so once I square everything, then I realize, because the square is just the summation of j delta j minus gamma j squared. And the constraint really says delta j is greater than aj smaller than bj, right? It's component wise. And I realize the problem is separable, meaning that I can solve each delta j separately, right? And to solve each delta j separately, I have a univariate problem. And because I have a univariate problem, I can use the theorem we mentioned before, right? I can use this theorem here. Okay, so just ignore the constraint, you find the minimizer, which is gamma, and then you just project gamma to your constraint, right? And then that gives you the solution. Okay, this is very simple because the problem is separable. That allows us to reduce everything to the univariate case. And the univariate case is very easy to deal with because we have a core theorem. Okay, the second example here is projecting to the Euclidean ball. Okay, so if I have a round Euclidean ball, and this is the origin, let's say, and if I take a point outside of the Euclidean ball, what is the projection to the ball? Well, following your intuition, you might guess the projection is just connecting this point with the origin, and then when you hit the boundary, that's the projection, right? This is our intuition, and it is indeed true. You can prove that. It's slightly more difficult than the previous example, and the reason is because the constraint here is not separable anymore, right? Because the sum of the square of all the coordinates is smaller than 1, so they depend on each other. The fortunate thing here is we can do a change of variable to make the problem separable again, right? So this constraint, by using this sort of a polar coordinates, right? So I'm assuming all of you know this. So if I have a vector like z, I can always decompose it as a magnitude and then a direction, right? So the direction is just z divided by z2 norm, and r is just z2 norm, right? So you have the magnitude and you have a direction. Okay, this is the usual polar coordinate decomposition. So we rewrite z as the product of the magnitude and the direction, and then we expand the 2 norm. You get the cross term. You get r z bar 2 norm squared, which is just r squared because z bar has unit norm, and w norm squared is a constant. I don't really care about this term. And then you realize now I can minimize the direction first. When I minimize the direction, r is just a constant, right? I don't really care about r. I only maximize this dot product. And when you maximize the dot product, we can use Cauchy-Schwarz inequality, and that gives you the optimal solution for the direction z bar. And then you plug in the optimal direction for z bar, you get a univariate problem for r. Okay, and then we can use our previous theorem to solve r, and then you put everything together, you found the projection. Okay, the projection is indeed a scaling of the input. Okay, so this is actually a cool result that shows that if the projection is always a scaling, then the set C has to be the Euclidean ball. Okay, this is actually a characterization of the Euclidean ball. All right, and I included 2 exercises here. This is for you to figure out these results, the solutions. It's fairly easy. So you should be able to do this very quickly. All right, so the next result I want to talk about is sort of the optimality condition for the projection. Okay, and so what this mean is, how can we verify if I give you a point, let's say I'm going to claim this point is a projection, how do you know if I'm telling the truth or not, right? And this is why we need these optimality conditions. You can verify things. And the first one here is nothing but the definition. And the second one here is very interesting. This one requires a constraint set to be convex. Okay, if you have a convex set, then we have W bar to be the projection if and only if this is true. Okay, and this is very important. I would recommend you to memorize this using a picture. So what it says is, I have a convex set C, I have my C, and then I have my W. Let's say W is outside. If it's inside, it's even easier. Okay, and then I'm going to project W, find the closest point, right? This is my W bar. And what this condition 3.4 says is basically you take any point in the set C. Let's say I'm going to take Z, any arbitrary Z, right? And then you connect Z with the projection, and you look at W, the input, and you connect them with the projection, and then you have a triangle, right? And this results here 3.4 basically says the triangle, and you have an angle here. This angle here is obtuse. Okay, I think I had a typo here. So this angle here is always obtuse. Okay, and geometrically this is very clear, right? So if I pick another point, you can see the triangle here. This is obtuse. If I take another one, right, the best you can do is to take a point here, and the angle is close to the right angle, right? So geometrically this is very clear, and the proof is also extremely easy. So you can read this in only 2 lines. So I'm not going to repeat it here because geometrically this is very clear. Okay, and you can also rewrite this inequality as this inequality here. They are exactly the same. So this one says the angle is obtuse, and this one here basically says the length. Okay, so if you look at the triangle, let's say if you have A, B, C, the length of each side, then there is a formula you must have learned maybe in middle school or maybe in primary school, depending on which country you're from. So C square is equal to A square plus B square plus 2AB, minus 2AB cosine of the angle here, right? And the angle is obtuse, so the cosine is negative, and therefore you have a positive here. Okay, therefore C square is greater than A square plus B square, and this is exactly what you see here. Okay, all right, so that's very clear. For convex at C, we have this obtuse angle here. All right, so now we understand projections. How do we develop an algorithm that can solve, that can minimize a constraint problem? The idea is extremely simple. It's actually what we have seen last time as well. So last time when we discussed gradient descent, what we did was we upper bound the function by a quadratic, right? Because the function is L smooth, so I can upper bound the function by a quadratic. Now then, instead of minimizing the function, I'm going to minimize the quadratic, and then I'm going to iterate this, right? You can do exactly the same thing and get projected gradient descent. So we have our function f of w, and I do a quadratic. I apply the definition of L smoothness, right? Now instead of minimizing the function over c, I'm going to minimize the quadratic function over c. Okay, so previously we didn't have the constraint, right? Now we just add the constraint. We just bring the constraint with us. Okay, and if you look at the term here, what do we have? Well, you have a common term, w minus wt, right? So if I rewrite, this one is going to be w minus wt and w minus wt, the dot product, right? And I'm going to combine the terms. I'm going to get, okay, maybe I don't need to do that. So let's just combine the terms. So I'm going to get w minus wt minus eta, sorry, theta f wt. So the first thing you do is you multiply everybody by eta t, right? That doesn't change the minimizer. And then you verify this term here is equivalent to this term up to a constant, okay? Because you have this, which is corresponding to this, and then you have a cross term corresponding to this term, and you have this term squared, which is a constant. We don't really care because it doesn't depend on w, okay? And then you minimize w over c for this function, and this is exactly the projection of this term to c, right? So this is our definition of projection. So that gives us the projected gradient descent algorithm. So basically, you do the usual gradient descent update, right? After you do the gradient descent update, you may go outside of the set C. Then you just project it back. Now you do the projection, so WT plus 1 will be in C, right? So if I draw a picture, basically we have a set C, and then you have, let's say you're here, this is a WT, and then you have a gradient descent step, right? And maybe you move to here. And then you're going to project back to the set C, and that's your WT plus 1. And then maybe you do another gradient step, right? And then you project, okay? So this is the idea behind projected gradient descent. All right, so that's very simple. This is the pseudocode for projected gradient descent. The only difference is from last time is we add a projection operator. Okay, so we do gradient descent and then we project and then we iterate. Okay, you cannot do it once, you have to iterate. All right, so that's good. And in fact, the projected gradient descent algorithm gives us a definition of stationarity condition. Okay, namely that if we iterate this gradient, projected gradient descent, and suppose W will converge to a W star, then W star will satisfy this equation here, right? And what we're doing here is we just take this equation and we say any point that satisfies this equation is going to be my optimal solution. Okay, to see why this makes sense, let's say C is the entire space. Okay, so if C is the entire space, we get the equation can be rewritten as W star equals projecting to the entire space. It's just not doing anything, right? So we have this, and then you cancel W star, you cancel eta, and then you realize this condition is equivalent as the gradient has to go to 0. Okay, and we use the vanishing gradient as the stationarity condition for unconstrained minimization. Now you can use this as a stationarity condition for constrained minimization, right? And the nice thing is I can actually measure this. Okay, so because what I can do now is if I have a candidate solution WT, and I can try to measure the gap, right, of this of WT satisfying this equation. So if this gap is 0, then I know WT satisfies this equation. But if this is not 0, but if this is decreasing, right, then I know the algorithm is making progress. And if you look at our definition here, then this is just WT minus WT plus 1. Right, so I can actually compute this because I'm doing this iterate. I have the trajectory. Okay, so this condition you can measure. So you can monitor how well this condition is satisfied, right? Okay, and then you can do some simplification of this equation here, especially when the set C is convex. When the set C is convex, because when C is convex, we had a characterization, right? We have this characterization of the projection to a convex set. So you can just plug it in, and then you can simplify this condition a little bit to this. Okay, and next week, we're going to take this condition here, and we're going to develop a different algorithm. Okay, so the point here is we started with the algorithm, and then we use the algorithm to define what we want for solving a constraint minimization problem. And then we can maybe develop a different algorithm that can satisfy this equation as well. Okay, and if everything is convex, this condition is actually sufficient and necessary. So if F is convex, if C is convex, then this condition is necessary and sufficient. Okay, all right, so now we know how to measure progress, and we have an algorithm. How does it do, right? Well, this is, first of all, if you look at how we derive the algorithm, if we go back, this is how we derive the algorithm. It's exactly the same as before. The only difference is we put a constraint, right? And it's not hard to imagine that we actually get the same guarantee as gradient descent. So as you can see, it's almost the same. The only difference is in gradient descent, we show that the gradient is vanishing, right? Satisfy this bound. But now for projected gradient descent, we have this term. Okay, and you can easily verify if C is the entire space, then the two are equal. Okay, so the result here is really a generalization of the one you saw last time, and the proof is exactly the same. Okay, so I'm not going to repeat. And also the remark we made last time, for instance, the Amijo's line search procedure can be applied in the same way as before. Okay, all right, so that brings me to the last theorem that I want to discuss. So this is a very important theorem. This is the first time you are going to see a meaningful convergence rate. Okay, and then we're going to derive this under the convexity assumption. So we're going to assume the function f is convex and L smooth. The constraint C is closed and convex. Okay, it's a convex set. And we have a step size. We're going to choose a step size using Amijo's rule. Okay, you can also choose the step size to be 1 over the L smoothness parameter. Then you run the projected gradient descent algorithm, and the claim is after t iterations, this function value f of wt is smaller than any f of w, so w here is arbitrary, plus w subtract the initialization divided by t and eta t bar. Okay, so eta t bar is the average step size we used. So if you choose a constant step size like 1 over L, then eta t bar is also 1 over L. Okay, So think of eta t bar as a constant. So the crucial thing is you have a t in the denominator. Okay, so that means if I run the algorithm for t iterations, then the function value will converge at or decrease at the rate of 1 over t. Okay, and the proof of this result is again extremely simple and elegant. So what you do is you use L smoothness as we did before. Okay, so this is the inequality. The only difference is in L smoothness, when you upper bound the function by quadratic, we have L over 2 here, right? So, and this is the only place where we have some assumption on the step size. So the step size, we choose the step size eta t such that this inequality holds. And we know if eta t is smaller than 1 over L, then this inequality holds. Right? We know that. But in practice, you might want to use Amijo's rule to use a bigger step size, right? All right, so this first one is easy. It's basically the definition of L smoothness. The second one, so the second inequality, let me explain that, and let me erase them. Okay, so what is the second inequality? Well, to see what we have for the second inequality, it's better to take this term here and rewrite as 1 over 2. So I'm going to multiply everything by eta t. So I have eta t here, I have eta t here. Okay, so I multiply everything by eta t. That will make it easier for you to see why this is true. And then I'm going to write this as wt plus 1 minus wt minus eta t and the gradient. Right? So I have the first term to be here. And I have the cross term to be here. The cross term is here. And then I also have, I need to subtract the remaining term. Oh, sorry, made a mistake. So I need to subtract the remaining term, which is eta t. Right? Okay, so that's good. And then you do the same thing for this term here. That will give you 1 over 2 and w minus wt minus eta t. And you're going to subtract the same thing. Okay, so that this term here is this. All right, so now what you need to do is to go back to our triangle here. Okay, remember we showed that this is obtuse angle. So you have the inequality of this. This inequality is exactly what we use here. Okay, so if you cancel these two terms, because these two terms are the constant, right? So wt plus 1 is a projection of this. Okay, and if you apply the result here, where w bar is wt plus 1 and w is actually w minus eta of that the gradient of w, and z is wt, I believe. Okay, if you do this, sorry, z is w and w is wt. Okay, let's make it precise. And if you do this substitution, you're going to get exactly this inequality here. Okay, and this is how we derive this inequality. Nothing magic. All right, and the last inequality follows from the convexity of the function f. So here, because this term, let me use a different color. So this term here, this term is smaller than f of w. Okay, this is a usual convexity definition. In fact, we actually proved this in the previous lecture within the Fermat condition, the necessary condition for unconstrained minimization. So we actually proved this inequality. So if you're not familiar, you can go back and check this inequality. Okay, and that's it. So basically, the first inequality, L smoothness. The second inequality is due to C is convex, the constraint is convex. The third inequality is due to the function f is convex. So you see, every assumption we made has been used. Eta t is used at here as well. Right, eta t is on the first inequality. So every condition has been used, which is good. Okay, so now the first thing we do is we set w, because w is arbitrary. W can be any point in the set C. So we'll set w to be wt, and then this is 0, and this is a negative term. So we know fwt plus 1 is smaller than f of wt, right? So this means the algorithm is monotonically decreasing the function value, okay? All right, once we have this, the rest is, we're almost done. So basically what you do is you realize this term and this term. You can telescope, right? So you just do a summation on t, and these guys will cancel each other. Okay, so what you end up, what you're left with is this term in the middle. This term is because we multiply everything by eta t. We multiply everything by eta t. And this and this, if you sum over t, you're going to get this term here. Okay? And these guys, when you sum over t here, they're going to telescope. So what you end up with is the first term and the very last term. And you're going to subtract the very last term, right? Because the very last term is also positive, so if I don't subtract it, I get something even bigger that justifies this inequality, okay? All right, so that's good. And then we use what we proved, that the algorithm is decreasing the function value. Therefore, this term here is greater than f of wt, the last guy, right? Because the function value is decreasing. And this is why you get the first inequality. Okay? And that's it. And then you just divide this to here. And then that is exactly the claim we had. Okay? And that's the proof. So basically, 4, 5 lines. It's extremely simple once you understand. And the interesting thing is, this very elegant proof was only discovered, I think, like 15 years ago. So not long ago. Okay? Well, whereas the algorithm was discovered in 1960s. So it's almost like 70 years ago. All right. So what does this mean? Well, this is the first result that you have seen under the convexity conditions. If you run projected gradient descent, then you can decrease the function value at the rate 1 over t. Okay, t is the number of iterations, right? So the more iterations you do, the more you can decrease the function value. And the rate is precisely 1 over t. Okay, this is not the best you can do. So in a few weeks, we're going to have an even better algorithm. But at least you know how to prove these convergence rates, right? There's nothing magical here. Okay, so all the inequalities we use, they're fairly standard. And the convergence rate depends on how far away your initializer is, right? Which is very natural. It depends on the L smoothness parameter, again, very natural. The important message, as we mentioned last time, is that the convergence rate does not depend on the dimension. And this is very crucial for data science or machine learning, because in machine learning problems, the dimension D is huge. Okay, and there's no dependence on the dimension D, so the algorithm might still work. Okay. Here I also mentioned that you can actually prove the iterate WT can converge as well. Okay, this is a little bit complicated, so we're not going to touch it here. All right, so that's the main result I want to discuss for this lecture. Okay, so basically we showed you the first convergence rate for projected gradient descent under the convexity condition. Okay, and of course, if you do not have any constraint, then projected gradient descent is just a gradient descent. So the rate will still apply for gradient descent as well. All right, so the last thing I want to mention is the so-called devil is in the details. Okay, you might think, oh, the projected gradient algorithm is so cool, right? It's so elegant for dealing with constraints. However, there's a catch. So the catch is that projection. So in projected gradient descent, you need to do projections at every iteration, and projection is itself a constraint minimization problem, right? We write everything as a one sort of a symbol you're projecting to a set C with input W, right? This symbol here is itself a constraint minimization problem. So how do you solve this projection? And you have to do this at every iteration, right? So this basically tells you can apply projected gradient descent and enjoy this 1/t convergence rate only when projecting to the set C is very simple. Okay, we give you a few examples where the projection, you can actually compute the projection in closed form. In these settings, you can apply projected gradient descent. Whereas in some other settings, projecting to the constraint is actually very difficult or very expensive, right? In those cases, even though you can apply projected gradient descent, but because the projection is so expensive, it may not be a good idea. Okay, so in fact, next week we're going to see another algorithm where we can deal with the constraint in an entirely different way. Okay, all right, so that's all I want to discuss for this lecture. For the assignment only depends on this lecture in a very, very minor way. Okay, so basically if you understand the two exercises we did, how to compute the projection, that's enough for you to do the assignment. Okay, so that's all I want to discuss. So I guess I will see you next time.